A power factor correction capacitor bank is a device available that is typically installed in parallel with residential loads. Most residential loads, appliances, and electronic devices draw inductive current, causing a lagging power factor. A power factor correction capacitor bank introduces capacitance into the circuit, generating a leading current. This leading current counteracts the lagging current, bringing the power factor closer to 1.0, which is unity. Improving the power factor diminishes the reactive power component of the current. Because only the real power component performs actual work, the decrease in reactive power leads to a reduction in total power consumption. The wattmeter disc is powered by the active or real power. As the power factor correction capacitor bank enhances the power factor, it diminishes the reactive power component and elevates the active power component. This causes the wattmeter disc to rotate faster. Aside from conserving power, power factor correction capacitor banks provide extra advantages. Firstly, enhanced voltage regulation. Secondly, decreased line losses. Thirdly, extended equipment lifespan. And fourthly, a smaller carbon footprint. It is important to know that power factor correction capacitor banks must be sized and installed by a certified electrician. Overcapacitation, which involves installing capacitors with too much capacitance, can result in overvoltage and harm to equipment. Some utility companies may impose penalties on customers with low power factors. Now let's dive into more detail regarding power factor, reactive power, real power, and apparent power. Power factor is a crucial concept in electrical engineering, particularly when discussing AC power systems. It's a measure of how effectively electrical power is being used. To understand power factor, it's helpful to first define a few related terms. Real power, also known as active power, is the power that actually performs work. It is measured in watts. Examples of real power usage include a light bulb emitting light, an electric motor turning a shaft, or a heater producing heat. Reactive power is the power that is stored and released in inductive and capacitive components of a circuit, such as motors, transformers, and capacitors. It does not perform any actual work. Reactive power is measured in volt-amps reactive, or VAR. Apparent power is the vector sum of real power and reactive power. It represents the total power flowing in the circuit, regardless of whether it's doing useful work or not. Apparent power is measured in volt-amps or VAR. Power factor is defined as the ratio of real power to apparent power. Power factor equals real power divided by apparent power. Since real power is always less than or equal to apparent power, the power factor is always a number between 0 and 1. A power factor of 1, also known as unity power factor, means that all the power flowing in the circuit is being used to do useful work, and there is no reactive power. A power factor of 0 means that all the power flowing in the circuit is reactive power, and no useful work is being done. In AC circuits, loads can be either resistive, inductive, or capacitive. Resistive loads, such as incandescent light bulbs and heaters, consume only real power. Inductive loads, such as motors and transformers, consume both real power and reactive power. The reactive power in inductive loads is due to the magnetic field that is created when current flows through the inductor. This magnetic field stores energy, which is then released back into the circuit. Capacitive loads, such as capacitors, also consume both real power and reactive power. The reactive power in capacitive loads is due to the electric field that is created when voltage is applied to the capacitor. This electric field stores energy, which is then released back into the circuit. Inductive loads cause the current to lag behind the voltage, while capacitive loads cause the current to lead the voltage. The power factor is said to be lagging when the current lags the voltage, and leading when the current leads the voltage. Most residential loads are inductive, meaning they have a lagging power factor. This is because most appliances and electronic devices contain motors, transformers, and other inductive components. A low power factor can cause several problems in electrical systems. Firstly, increased current flow. Secondly, increased losses. Thirdly, reduced capacity. And fourthly, voltage drop. Let's look at each of these in more detail. A low power factor means that more current is required to deliver the same amount of real power. This is because the apparent power is higher than the real power. The increased current flow can overload conductors and equipment, leading to overheating and potential failures. Increased losses result when a low power factor causes increased current flow, which leads to higher I2R losses in conductors and equipment. These losses waste energy and increase operating costs. Reduced capacity is when a low power factor reduces the capacity of electrical systems. This is because the increased current flow takes up more of the available capacity. Voltage drop is when a low power factor can cause voltage drops in electrical systems. This is because the increased current flow causes a larger voltage drop across the impedance of the conductors and equipment. Power factor correction is the process of improving the power factor of an electrical system. This is typically done by adding capacitors to the system to counteract the effects of inductive loads. Capacitors generate reactive power that is equal and opposite to the reactive power consumed by inductive loads. This cancels out the reactive power, improving the power factor. Power factor correction can be done at individual loads such as motors or at the main service entrance of a building. Power factor correction capacitors are rated in kilovars or kVAR. The size of the capacitor bank required depends on the amount of reactive power that needs to be corrected. A qualified electrician can determine the appropriate size of capacitor bank for a particular application. Power factor correction offers several benefits, including reduced energy costs, increased system capacity, improved voltage regulation, and reduced equipment losses. By improving the power factor, less current is required to deliver the same amount of real power. This reduces I2R losses in conductors and equipment, saving energy and lowering electricity bills. Power factor correction frees up capacity in electrical systems. This allows more loads to be added to the system without overloading it. Power factor correction improves voltage regulation by reducing voltage drops in the system. This helps to maintain a stable voltage supply to loads, which can improve their performance. Power factor correction reduces equipment losses by reducing the amount of current flowing through the equipment. This can extend the life of the equipment and reduce maintenance costs. While power factor correction offers many benefits, it is important to consider the potential drawbacks as well. Overcorrection, which means installing too much capacitance, can lead to overvoltage conditions. This can damage equipment and create safety hazards. Resonance can occur when capacitors are installed in systems with harmonic currents. This can amplify the harmonic currents, leading to equipment failures. Switching transients can occur when capacitors are switched on and off. These transients can cause voltage spikes that can damage equipment. It is important to consult with a qualified electrician to determine the appropriate type and size of power factor correction equipment for a particular application. The electrician can also ensure that the equipment is installed and operated safely. In addition to using power factor correction capacitors, there are other ways to improve the power factor of an electrical system. These include using energy-efficient motors, avoiding lightly loaded transformers, and minimizing the use of inductive lighting. Energy-efficient motors have a higher power factor than standard motors. This means that they consume less reactive power and deliver more real power. Transformers operate most efficiently when they are fully loaded. When transformers are lightly loaded, they consume more reactive power and have a lower power factor. Inductive lighting, such as fluorescent and high-intensity discharge lighting, consumes more reactive power than other types of lighting. Replacing inductive lighting with LED lighting can improve the power factor of the system. Now let us discuss more deeply about inductive loads. Inductive loads are electrical loads that primarily consume reactive power in addition to real power. This is due to the presence of inductors, which are components that store energy in a magnetic field. Examples of inductive loads include motors, transformers, and fluorescent lighting ballasts. Inductive loads cause the current to lag behind the voltage in an AC circuit. This lagging current reduces the power factor, which is a measure of how effectively electrical power is being used. A low power factor can lead to several problems, including increased energy costs, reduced system capacity, and voltage drops. Motors are one of the most common types of inductive loads. They are used in a wide variety of applications such as pumps, fans, compressors, and machine tools. Motors consume reactive power to create the magnetic field that is necessary to rotate the motor's rotor. Transformers are another common type of inductive load. They are used to step up or step down voltage levels in AC circuits. Transformers consume reactive power to create the magnetic field that is necessary to transfer energy from the primary winding to the secondary winding. Fluorescent lighting ballasts are used to regulate the current flow to fluorescent lamps. They also consume reactive power to create the magnetic field that is necessary to start and operate the lamps. The amount of reactive power consumed by an inductive load depends on the load's inductance and the frequency of the AC power supply. The higher the inductance and the lower the frequency, the more reactive power the load will consume. Power factor correction is the process of reducing the amount of reactive power consumed by inductive loads. This is typically done by adding capacitors to the circuit in parallel with the inductive loads. Capacitors generate reactive power that is equal and opposite to the reactive power consumed by the inductive loads. This cancels out the reactive power, improving the power factor. The size of the capacitor bank required depends on the amount of reactive power that needs to be corrected. A qualified electrician can determine the appropriate size of capacitor bank for a particular application. Power factor correction can be done at individual loads, such as motors, or at the main service entrance of a building. Power factor correction offers several benefits, including reduced energy costs, increased system capacity, improved voltage regulation, and reduced equipment losses. By improving the power factor, less current is required to deliver the same amount of real power. This reduces I2R losses in conductors and equipment, saving energy and lowering electricity bills. Power factor correction frees up capacity in electrical systems. This allows more loads to be added to the system without overloading it. Power factor correction improves voltage regulation by reducing voltage drops in the system. This helps to maintain a stable voltage supply to loads, which can improve their performance. Power factor correction reduces equipment losses by reducing the amount of current flowing through the equipment. This can extend the life of the equipment and reduce maintenance costs. Now to discuss capacitor banks. Capacitor banks are collections of capacitors used to store electrical energy. They are widely employed in various applications, particularly in power systems, to improve power quality, correct power factor, and provide voltage support. A capacitor bank consists of multiple capacitors connected in series or parallel to achieve the desired voltage and capacitance ratings. The capacitors are typically housed in a metal enclosure and equipped with protective devices, such as fuses and circuit breakers, to prevent damage from overcurrent or overvoltage conditions. Capacitor banks are used in a variety of applications. Firstly, power factor correction. Secondly, voltage support. Thirdly, harmonic filtering. And fourthly, energy storage. Let's look at each of these in detail. Capacitor banks are commonly used to correct power factor in electrical systems. Inductive loads, such as motors and transformers, consume reactive power, which causes the current to lag behind the voltage. This lagging current reduces the power factor, which is a measure of how effectively electrical power is being used. Capacitor banks generate reactive power that is equal and opposite to the reactive power consumed by inductive loads. This cancels out the reactive power, improving the power factor. Capacitor banks are also used to provide voltage support in electrical systems. When the voltage in a system drops too low, capacitor banks can be switched on to inject reactive power into the system. This reactive power helps to raise the voltage back to its normal level. Capacitor banks can also be used to filter harmonic currents in electrical systems. Harmonic currents are unwanted currents that can cause problems with electrical equipment. Capacitor banks can be designed to filter out these harmonic currents, improving the power quality of the system. Capacitor banks can be used to store electrical energy. This energy can be used to provide backup power in the event of a power outage or to improve the efficiency of electrical systems. The size of a capacitor bank depends on the application. For power factor correction, the size of the capacitor bank is determined by the amount of reactive power that needs to be corrected. For voltage support, the size of the capacitor bank is determined by the amount of voltage support that is needed. For harmonic filtering, the size of the capacitor bank is determined by the amount of harmonic current that needs to be filtered. Capacitor banks can be installed in a variety of locations such as substations, industrial plants, and commercial buildings. They can be installed indoors or outdoors depending on the application. Capacitor banks are typically controlled by automatic switching devices. These devices monitor the voltage and current in the system and switch the capacitor banks on or off as needed to maintain the desired power factor, voltage, or harmonic filtering. Capacitor banks are a valuable tool for improving the efficiency and reliability of electrical systems. They can help to reduce energy costs, improve power quality, and provide voltage support. It is important to consult with a qualified electrical engineer to determine the appropriate type and size of capacitor bank for a particular application. The engineer can also ensure that the capacitor bank is installed and operated safely.